All right, so welcome back. Welcome back to the channel. So in this video, so in the last few videos, we have been learning about this model NextGPT, which is a multi-model LLM through which like we could we could have our language model to be to consist of uh, multiple features or multiple inputs, right? It could deal with multiple functionalities or multiple modalities, right? We could have multiple modalities, and the model could understand patterns and uh, it could essentially have let's say you are having a conversation, right? You could also add in images, and the model could understand the text in the context of maybe the image, right? So that is a idea of it, to be able to like encode all the information, all the modalities into a single form where the model could understand similarities in that one single form, which will be converted by the encoder, right? I think we use some encoder here called I forgot the name. Just look at it. Yeah, image bind, in which we'll encode. We could, using this encoder, I think it's a train encoder through which we could access uh, the encoders through which we could encode all our modalities. Here in this paper, we use the modalities of images, video, text, and I think audio, right? So these are the main all the things that we will be encoding using this image bind. Again, if you want, I think a deeper look into the architecture of how this works and other useful tools, I definitely do recommend you to check everything out. Check the last video. I think last video is the only one, which is enough for you to understand everything. Even though you don't have to have a huge understanding of deep learning. You don't have to have a experience, and like you don't have to understand the basic deep learning, but I think I have explained it in a pretty easy and interpreted manner, I hope. So that is the last video. I'll just give you one more, just like a recap of what we have done in the last video. That again, this is a recap. I'll not be going into the depths. I'll make so this is going to be a little video, a short video in which we are going to learn. We're just going to look at other things that they have told in this paper. Right. So we'll be doing that first. First of all, multi-modeling. Of course, multi-modeling is about taking data of different modalities and interpreting them or converting them into the same form such that the model can find features in that one single form. Right. So we're going to have something called encoder. Encoder is going to consist of which is we're just going to encode these representations. Again, we are going to use something called image bind. So this image bind uses something called encoders, which I have shared in the last video. So again, we'll take some modalities, for example, images and text. Let's say we're going to encode these images into some kind of representations, right? For example, text representations. And we're going to do the same for videos also. And we're going to basically have some text representation for that specific video. And to make this text more understandable, right? Because we have to have like some kind of workflow, right? We want to make this text understandable to the LLM, right? So therefore, we have to do some. We have to make sure the encoder, right? Make sure the encoder uh, makes the text in the form that an LLM can understand, a large language model can understand, and that is essentially alignment, which we will study, which we'll understand in just a minute. And then after that, we're going to have image input projection, in which we are going to have a simple dense layer or just a simple neural network in which we are going to project these input representations into a much more understandable form for the LLM. Right, and then same after we could have multiple images, right? And then we could have we would represent images, audio, and video with separate tags. Let's say, anyway, both all of them are like numbers, right? So we'll pass these data into the encoders, and we'll get the corresponding data, and then we will represent each data with I think a specific tag or a specific signal or something, and then we could pass them all of them to this large language model. And output of the language model, well, if the model thinks that there is a need to output an image, then the model predicts a image tag. It predicts an image tag with some kind of description of how that image looks, and that is essentially going to be the prompt of a diffusion model, right? We're going to also employ a diffusion model for all image, audio, and video to produce that specific output. For example, producing an image, producing audio, or producing a video. right? And then yeah, so we are going to use diffusion model, pre-trained diffusion models. Again, there is a lot of work going on in every field. There is a lot of work that has been going on in diffusion field. I've also made some videos on diffusion. Check them out if you're interested. And then we'll essentially like prompt these diffusion models based on what. So the model will learn to prompt these diffusion models to get the required images, right? Images, videos, and audios. Based on what the model needs to generate. Right. So that is the basic idea. That is what is happening here. Again, the encoders, the projection layers, in which the model will not make images in a format that the model, the output, the images, for example, or the audio and video will be converted into format in which an LLM can understand, and um, the output will be also be some product projection, which is also learned. Right, the model will try to learn something to predict something for images, audio, and diffusion video. So and then essentially we'll pass all this into some diffusion models to get the output. Again, this is going to be random text. For example, the model has to generate, let's say, a photo of MS Dhoni. Right, let's say the model has to generate a photo of MS Dhoni in the completion or in the output. Then the model will let's say give a prompt. For example, MS Dhoni hitting six in the 2011 Sri Lanka final, right? Yeah, in 2011 against Sri Lanka in the World Cup, or something like that, right? Maybe new photos or something, anything, right? And then we could pass this prompt to the diffusion models, and the diffusion models would get us the output image. And then alignment. So alignment basically helps us to bridge the gap, to cover up the gap between these between all these tasks, right? There is a lot of gap, right? The output of, let's say, the output of encoder should be able to be easier for the model to understand. So that is one gap that we have to fill. We add this image input processing, and also the other gap is to make sure the output of the model is understandable to the diffusion model, right? So the output of the prompt is better enough, right? So these are some gaps that we have to bridge, right? So that essentially is alignment. That is alignment. I'll just go to this part, alignment. So we'll just read through that and try to understand what is this. So following the common practice of existing LLMs, we consider aligning different inputting multimodal features with the text feature space. The representations that are understandable to the core LLM. This is thus intuitively named the LLM-centric multimodal alignment learning. To accomplish this alignment, we prepare the X caption pair. All right, X stands for image, audio, or video, data from existing corpus and benchmarks. We enforce LLM to produce a caption of each input modality against the gold caption. All right, we enforce them to produce a caption of each modality against the gold caption. Yeah, so yeah, this is essentially the learning process I have shared in the last video, right? We're going to have some. So yeah, we have a lot of data on the internet. Number one. So we are going to have a lot of pairs of image caption data. And then the model has to generate that caption, right? I've shared the idea of encode on the last video. I'll probably try to make maybe a new video on that, just to make sure you could come back to it whenever necessary. That is probably a good idea. But think of the encoder just like I'm going to go to the whiteboard. Just going to give you a brief overview. So let's say you have an image, and then there is going to be a specific caption for that image, right? There is going to be some type of caption for that image, and then the model will basically like take this image, and maybe it'll pass through a separate neural network. We'll take this text also in some type of neural network, and again, this neural network can be any pattern recognizing network, maybe in the future, or anything, right? Any pattern recognition feature for that specific data, of course. It's image data, and the model will be, the model will predict some vectors. Again, here I will describe the learning process in just a bit, and then this also is going to return a vector, let's say. And then what we're going to do is we're going to get the dot product. We're going to get the dot product. Again, this is the training data, right, for each pair. So let's say this is the first pair, and then we're going to get the dot product of both of the vectors, and then the loss function right? The loss function is designed in a way such that the higher the dot product, that is the more similar these vectors are, the lesser the loss function, right? And the more different the vectors are, the higher the loss function. And the difference and similarity can be captured by dot product, right? So we'll be calculating the dot product between the vectors of these neural networks, and we're going to calculate the loss function. And through this loss function, we're going to update the weights of this or the parameters of these neural networks, both of these neural networks. Right, so that is the idea. That is a simple learning process of this model. So the model will try to generate the caption based on the input, and that is exactly what we'll be doing for the encoding stage. Right, for the encoding stage, we're going to get this image. We're going to have to find a way to represent it in some text, right? So that is what we'll be doing, and as that is the thing that has been shared here, right? We're going to have some input image representation, and there's going to be some caption. We're going to, so based on this caption, based on the loss function, based on how similar our caption is to the actual caption, and yeah, so basically, like we train this model. So basically, we just train this model, and this is going to be this model. We're going to predict the caption, and my bad, we don't train this neural network. I don't think we'll, I mean, we don't have to train this neural network. I mean, we could use like a pre-trained model which already has some kind of understanding of what text is, and based on that, this model will, there'll be some notion of this model, understanding this model, right? Just like I think a student teacher experience here. I mean, there is some kind of notion of that. I mean, right. So that is the idea here. We're going to update these representations, update these weights or parameters, and such that the caption is as closer. So yeah, I mean, we have, or we want to make sure that that this vector contains the meaning of the caption, right? I mean, we just want to make sure the meaning or the meaning is similar. That is the basic idea of this model. And then we'll be generating text, right? So we could just have a language model, or some it'll just be some like multi-class classification problem in which we'll select each word to predict the caption, and then we're going to do the same for all the models, and we'll have a learning, and we have some training to do. And then the decoding side, instruction following fine alignment. On the decoding end, we have integrated pre-trained conditional diffusion models from external sources. One main purpose is to align the diffusion models with LLM output instructions. However, performing a huge scale, a full scale alignment process between each diffusion model and LLM would entail a significant computational burden. Alternatively, we here explore a more efficient approach, a decoding side instruction following alignment, as depicted in figure 3b. Specifically, since different models of various modalities are conditioned solely on textual token prompts, this conditioning diverges significantly from the model signal token from LLMs in our systems, which leads to a gap in the diffusion model's accurate interpretation of the instruction from LLM. Thus, we considering minimizing the distance between the LLM's model signal token representation and the conditional text representation of the diffusion models. Since only conditional text condition encoders are used, the learning here is merely based on the pure captioning text, that is without any visual or audio resources. This also ensures highly lightweight training. Again, pretty basic words, right? Here, rather than having to do to encode from images to text, rather than doing that, we'll we'll just do a we'll just encode text into text. So basically, we'll just update our prompt, update the model, update the model's ability, or improve the model ability in prompting the diffusion model. So that is basically what we're doing here. And basically, yeah, we'll have a neural network. Again, we'll have a neural network, just normal neural network. And then we will be passing the text, right? We'll be passing our text, whatever the model generated, whatever the signal the model generated. So again, one more thing that is mentioned here is that we use the like the same text for all the modalities. I mean, the same format for all the modalities, text. And then we're going to have some signal, which is the tags based on specifying like what should be generated, either image, video, or audio. And then based on the tags, we'll pass them through that specific maybe model. So basically, we'll make sure the model generates new prompt by training it to give better prompts, right? So each image I think is going to have some caption, and we're going to make sure the model generate a closer caption, right? We could design like probably n number of architectures here for doing that one. One example is just giving this using something called maybe something like Siamese network or something. Maybe yeah. I mean, we could use the same architecture here. We could use let's say one neural network here and one pre-trained neural network, which also will. Uh, I mean, yeah. I mean, I think, or we could just look at this as like a multi-class classification task in which the model is like forced to predict the next word, or the model is made to predict the next word, just like a normal transformer, just like a normal language model. We could do that also, right? So that is, we will do that. We'll just train let's say a language model, a small language model. Back in the days when we don't have when we did have large language model, we would train language models for a specific problem, right? Here also we could have a small language model, maybe trained on this task, right? And maybe we'll do that, right? So that is the idea. That is the idea of alignment, and there is one more section which we will also look at, which is modality switching instruction tuning. Again, instruction tuning is, I think, a pretty simple idea, which I think most of you would have an idea of what that means. And then we have instruction dataset, which is the dataset that is used. So we'll just try to read through this, try to understand what is happening. All right. So instruction tuning, despite aligning both the encoding and decoding ends with the LLM, there remains a gap towards the goal of enabling the overall system to faithfully follow and understand users' instructions and generate desired multiple outputs. To address this, further instruction tuning (IT) is deemed necessary to enhance the capabilities and controllabilities of LLM. IT instruction tuning involves additional training of overall LLMs using input-output pairs, where input represents the user's instruction and output signifies the desired model output that conforms the given instruction. Technically, we leverage LoRa. LoRa, I think, lower rank or something. I mean, we will also read to that in just a minute, to enable a small subset of parameters within NextGPT to be updated concurrently with 2 layers of projection during IT phase, right? As illustrated in figure 4, where when an IT dialog sample is fed into the system, the LLM reconstructs and generates the textual context of input and represents the multimodal content with the multi-modal signal topics. The optimization is imposed based on code annotations and LLM outputs. In addition to the LLM tuning, we also fine-tune the decoding end of NextGPT. We align the multimodal we align the model signal token representations encoded by the input projection with the goal multimodal caption representation encoded by the diffusion condition encoder. Thereby, the comprehensive tuning process brings scores closer to the good goal of faithful and effective interaction with users. So again, nothing new. So basically, yeah, I mean, we just do the training process that they have shared here, and rather than like doing the full fine tuning, in which we'll just get the whole model, right? We'll just get the full language model and train all the models weights for doing this. Rather than doing that, we'll carry something called LoRa, right? So what is LoRa? And again, right, one more thing is we are going to train this language model again. We're going to fine tune the language model again. So because there aren't a lot of language models for the task of multi modeling, for the task of multi modeling, right? There has been a rise in the building of language models, but maybe not so much in the field of multi modeling, because I think it is a pretty new field. So basically, we'll take the existing language model, I think, which is here is Vaikun or something, and then we will fine tune this model. We'll not do full fine tuning. We'll just do something called LoRa, which I will describe in just a minute. Don't worry. Right. So we'll just rather than doing the full fine tuning, rather than updating the whole weights, so we'll make the model train or partially train or fine tune on our data, right? Whatever data that we'll be needing. So there is a lot of information on the internet, which has, let's say, text and videos and images combined in one form, and this makes sure the model understands the relation between like when to use text, when to use images, when to use images, audios, and the model can maybe understand the world better, or understand this thing called multi-modeling better, right? So that is the basic idea of using fine-tuning this LLM for this specific multi-modeling tasks, right? And then so I think that's it, right? What is LoRa, right? So I'll just basically give you a small idea of what that is. I'm not going to go into the depths of it, but I'm going to cover it very fastly, and I'll probably make another video specifically on this like other techniques along with LoRa maybe in the future. So yeah, so we don't have a neural network, right? Let's say transform a neural network for language modeling, and we're gonna have a bunch of weights, right? We're gonna have a bunch of weights, and then let's say we have some matrix, some kind of matrix, some kind of large matrix. Let's think of this as a matrix. So rather than updating all the weights, rather than performing gradient descent and calculating the maybe the gradient and updating all of them, rather than doing all that, we'll basically have some very small vectors or matrices, right? We'll have some very small matrices, and basically we will so for like every weight, for like every matrix, for every weight matrix, we'll have this maybe small, very small, like compared to the large matrix, it will be I think very small, and then we'll update these more right? We'll update these parameters, right? We'll update these parameters during training, rather than doing it for all the pre-trained models. Again, remember, for doing fine tuning, we have to have a pre-trained model which is already trained on large data, maybe found on the internet, and then we would create this random randomly initialized matrices, two matrices, and basically we'll be like updating all these weights of these matrices, and we will just multiply I think both of these matrices. We'll do some we'll do the matrix multiplication, and we'll just add this output to the actual parameters that is in the model. And during the training process or during the fine-tuning process, we'll only update this parameters rather than this. And I think it led to like 85% decrease, I think, in one problem. I have read I have read somewhere, it doesn't I think it resulted in like 85% lesser computation, which is absolutely amazing. Right, so I think it is way better. The fine tuning process will be very good. And again, we could also use maybe other larger language model than Vicuna or this class to maybe improve the performance. That gives us the flexibility to add maybe larger model, right? Right, and that is I think that is LoRa. That is what LoRa is. And yeah, that is so basically we'll just take all this data on the internet, and it'll pass all this data through this encoder. So encoder, I will just encode them. So we encode the images using the image encoder, audio using the audio encoder, video using the video encoder, and then the LLM. Well, the LLM, we're going to fine tune the LLM such that it could understand the captions, right, or the outputs, right? And also we're going to do that for the decoder, and also we're going to train the model, right? We're going to have some kind of cost entropy. So we'll essentially we will train the model again. We'll train the model for the decoder side also. We'll instruction tune for model video output also. So we'll just make sure the model's output is aligning to the actual output, right? Using some kind of cost entropy, determining the distance or closeness between both of these text. Right, and then the instruction data set, nothing new here. So how do we have the data? So we have text plus X data, which is we have the text captions, and let's say images separately, video separately, audio separately, like that. And then we have the text plus X data, which is I think text to multimodal. Yeah, we're gonna have X caption pairs. So yeah, I mean text and X data, some captions and some image and audio data. And here we have something called Mosaic data, I think it's a specific data set. I'll just look at it, what that is. So yeah, I mean text and X data, some captions and some image and audio data. And here we have something called Mosaic data, I think it's a specific data set. I'll just look at it, what that is. Put that in caps lock. Well, I guess it is not that popular. Yeah, yeah, maybe the data set is not that popular. All right, anyway, right. So we are gonna have this Mozit data, which is I think a specific data set in which we propose a novel modality switching. Mozit not only supports complex cross model understanding and reasoning, but also enables sophisticated multimodal content generation. So basically, we have everything what we need. We have to train the model on like decoding side and encoding side, right? So we don't have whatever we need. We're going to have in this model, in this data, and then we could find like use this data for all our tasks, which is quite good. And I think that's it, right? We're going to collect our data from many tools, YouTube, and yeah, something like that, and maybe stable diffusion, maybe previous examples. And we have some metrics here. Maybe we could determine. Maybe just look at these metrics. Maybe there are some instructions, right? So yeah, I mean, we could like look at the instruction, performance. When the model is given text and is made to predict the output and output as image and audio, right? When the model is given text and output will be image and audio, the performance is about like not that high. And when the model is like given more inputs, well, the performance is getting higher. And I mean, you can look at it, right? A here means audio, V here means video, and here the highest performance goes to this text and audio producing that image. Quite good. Yeah, so that is it. That is it for this video. Hopefully you have got an idea of maybe yeah, got an idea of the technique of alignment and some more. Yeah, maybe just like a wrap up for multi-modeling or NextGPT. So thanks for watching. I will so yeah, I will see you in the next video. Right, sorry.